In this lesson, we're going to talk about population, samples, and hypotheses. So just a few definitions to start us off. And you've heard me say population sample before when we talked about standard deviation, so we'll get a little bit deeper insight into what that actually means. So a population is a collection of all data, such as responses, measurements, counts, or whatever you want information about. So a quick example of a population could be like all the colors in your crayon box, okay? So that's everything contained in your box of 128 colors or something like that. Then we have a sample. So a sample is just a subset, like a snapshot of that population. So for example, if we go back to your 128 colored crayon box, maybe you take out 5 of them and you've got red, yellow, orange, blue, and purple. Those 5 colors are a subset of the population of that whole 128 different crayons in your box. So the idea is, if you think about a Venn diagram, you've got, let's say this is your population. Actually, maybe it's better if you just look at the circles rather than the whole mat. So if this is your whole population, then a little circle inside of it, that's a subset. It has to be completely contained in the population. It's not going to intersect. It has to be contained in it. So like if you're looking at all the different types of apples, you're not going to throw an orange in there because an orange is not part of the population of apples. Okay, so that's the idea of population and sample. And what's really important for us is if we're working with a sample, because it's often very hard to survey or get information about an entire population. So again, going back to the 2020 census of America, can we really go and get information from every single person who lives in the United States? No, right? It's going to be very difficult, a lot of manpower, and by the time we get everyone's information, it'll probably be time for the 2040 census or something, right? So we use samples then to help represent the population, but the key piece here is your sample has to be representative. Otherwise, your data is flawed. So when the sample is not representative, the conclusions are not going to be valid. So if you think about, let's say you want to do a survey of all the students at school, and you're saying, okay, well, I'm just going to survey the 9th graders and say that's everyone's opinion, but then you've alienated the 10th, 11th, and 12th graders. So only the 9th graders would not represent the entire population of the entire high school. So that's where we have to be careful to watch out for biases and make sure what we do is actually valid. Also something to think about, because you see stats all over the news and in the world, and you want to make sure you're asking these questions too, right? Are the conclusions they draw valid or invalid based on what you know? So I digress. So what we want to do is make sure we understand the idea of population and sample. So in the first example, we're just going to identify what is the population, identify the sample taken out of that population, and then we want to do a couple sentences or one sentence describing what the sample is. So first, if we look at the situation, the owner of a dance studio asks 32 dancers what their favorite type of dance is, and 25 of them say hip hop. So if you're thinking, okay, well, this owner is trying to find information about what? Well, the owner is the owner of a dance studio, and he or she is trying to figure out the dancer's favorite type of dance, right? So probably going to want to figure out everybody in the dance studio. Sorry, that's a little hard to read. So all dancers. Now, did this owner get to talk to all of them? No. This owner only talked to 32 of them. So when I read through that, that's what I got out of it. So the owner is probably trying to figure out what all of his or her dancers like, but only got around to asking 32 of them. And 25 of those 32 said hip hop. So we're going to go ahead and just identify the population and the sample. So there you go, there's the population and there's the sample. And next we want to describe what the sample tells us. So what information did we or the owner glean from the question? Well, the owner knows 25 of them, of the 32 liked hip hop, which tells us then 7 did not. So that, we want to be careful with drawing conclusions. That's what we actually know. Okay, so we know 25 of them liked hip hop and the other 7 do not. So there we go. Again, 2 parts to that problem. So describing that sample, we want to be careful. Don't get too crazy with your, I guess, conclusion you're drawing for that. Just kind of take it at face value. With stats, we do want to interpret the numbers, but first we want to think, what do the numbers actually tell us? So here the sample consists of 25 dancers who said their favorite type of dance is hip hop, and 7 who didn't, right? So that's kind of face value what it tells us. So if we take a look at the second example here, a counselor at Easton Middle School pulled 225 class schedules and found that 46 of them have science first period. So again, coming back to, what do you think we're trying to do with this study? Why is the counselor even pulling class schedules? So if their counselor is looking at schedules and trying to make any kind of conclusion, it's probably about all students, right? So we're looking at Easton Middle School. Oops, I was using the wrong color there. Easton Middle School students, right? So that is most likely my population. And, well, how many of them did the counselor actually get to look at? Just 225. So there's my subset. All right, so we can go ahead and identify the population in the subset first, and then we'll talk about what that actually tells us. All right, so there we go. The population is all the students. The sample is just the 225 student schedules that the counselor looked at. And what did the information tell us? Well, it tells us of the 225, 46 of them had science first period, which means 179 did not, right? So that's, again, the face value kind of information we got from this survey or from this sample data. And there we go. So that's the description of the sample. We want to be very careful. Again, we're not interpreting this. We're not saying, oh, well, that means a lot of people have science first period or whatever. We're just saying, okay, that's what we got from the survey. And then what we want to do is take that raw data and eventually do some testing with that and come up with interpretations and conclusions. But for this particular example, we're just saying what we have. Okay? So next we're talking about characteristics here. So a numerical description of a population characteristic called a parameter. It's called a parameter, I should say. So a numerical description of a sample characteristic is called a statistic. So I know we talk about statistics a lot, right, as what we are doing. And we do that because, like I said before, it's really, really hard to actually calculate parameters. Because can you get out there and count every single piece of information for an entire population? Probably not. Like if you're doing marine biology and you want to make some generalization about all populations, all bottlenose dolphins, are you actually going to be able to find every single one of them out in the wild? No. So we often talk about statistics because we work with a sample to give us a statistic, which then we can conclude parameters from if it's something that, you know, the sample can is representative enough to generalize to a population. Okay. So like I said, populations can be so large, so some statistics are used to estimate the parameter. Okay, so what we want to do next is, again, to make sure we understand the difference between parameter and statistic. And a couple things for notation, just so we are clear. Just like I mentioned before, we had different notation for sample standard deviation with the S and population standard deviation with the lowercase sigma. We also have notation for sample mean, sample proportion, which we'll talk about using in a bit, and also population mean and population proportion. So let me just write that down for you, just some notation to know. So mu is actually our population mean. And then P is what we call a population proportion, which we'll see in just a bit. And then if we're dealing with the sample, X bar, which you've seen me use before, is technically your sample mean. And then P with this little hat above it is called the sample proportion. And again, it's important for us to know the difference between population and sample here because we're talking about statistic versus parameter. And then we'll talk a little bit more about the proportion in a bit. So if we take a look at the first example, for all teenagers in a certain town working jobs last summer, the mean hourly wage was $6.95. Is the mean wage a parameter or a statistic? And then we want to explain our reasoning. So really, the big difference between a sample and a population is one a subset or is one all? So that's really what I look for. So in the directions, you might realize, wait a minute, it says all teenagers. It doesn't say, you know, just 25 of all of our teenagers. So when it's dealing with all, I'm going to trust that that means this is a population characteristic. So that means this is a parameter. So let me just kind of put in my thought here. So that's a population characteristic. Because of that word all, right? So that's kind of the key terminology I'm looking for. So using, if we needed to, and this is just a side note here, this we would label as mu rather than the next bar. Okay. So let me just write down my answer there. So again, I'm saying it's a parameter because we're dealing with all. So it's the entire population. All right, so there you go. That's my sentence there. The mean wage of $6.95 is a parameter because, like I said before, it's based on all. It's that population. So if we look at the next example, a survey of 912 men ages 50 to 60 in Central America found that the standard deviation of the length of their feet is about 4 centimeters. Is that standard deviation a parameter or a statistic? So remember what I was saying before, we're looking for all to represent population. Otherwise, if it's just a selection of them, then it's going to be a sample, which is a statistic. So key things to look for. If we're doing a survey, unless it says we survey all, it's most likely going to be a sample. You can also use a bit of logic too, because if you're saying, wait, they could have surveyed all, think about it. Do you think there's really only 912 men aged 50 to 60 in Central America? So in all of those countries from Panama, right, Costa Rica, Ecuador, El Salvador, all of those only have 912 men all put together that are 50 to 60? No way, right? So we know this is going to be a sample characteristic. So that makes this a statistic. There you go. So there's my explanation. So that standard deviation is a statistic. And remember, here's where we have to be careful. If we want to do anything more with that statistic, we have to make sure that sample was representative of all 56-year-old men in Central America. So on a tangent here, if I were to try to interpret this information, I would want to make sure when I look at the population of men, did they only take the men from a big city? Do they have an equal distribution of men living in metropolitan areas and rural areas? And these are all things you want to think about. But be careful when you start going down that rabbit hole, you start distrusting all statistics. So there's a time and place for statistics, but you want to make sure you are questioning them to make sure it does make sense to generalize if you need to. Okay, onward. All right, so next we want to talk about hypotheses. So a little different from the hypotheses you guys probably test in science classes. So in stats, a hypothesis is a claim about a characteristic of a population. So it's basically something you might get from a study of a sample, and then you want to broaden that and say, okay, well, I think that's true for the entire population. So you're trying to make that a parameter without, being able to state for sure it is a parameter, if that makes sense. So for example, if you look at these 2 bullet points, a drug company claims that patients using its weight loss drug lose an average of 24 pounds in the first 3 months, right? That's a claim. We don't know it's for sure true. The next one, a medical researcher claims that the proportion of US adults living with one or more chronic conditions, such as high blood pressure, is about 45%. Again, that's a hypothesis. It's not substantiated with any evidence, right? So it's a claim that we think this company thinks is true about the entire population. So in order to analyze the hypothesis, we have to be able to tell between results that could be, coincidental, happen by chance, or results that are really unlikely to happen by chance, and it was probably happening because of some reason. So one way we can analyze a hypothesis is to perform what we call a simulation. And it's basically kind of like an experiment. And when the results are highly unlikely to recur, the hypothesis is probably false. So we're going to run a simulation to basically test a hypothesis. So if we take a look at this example, we're going to roll a 6-sided dice, normal dice with faces 1 through 6, 5 times. And what we noticed is when we rolled that dice 5 times, we never got an even number. We got like 1 or 5. The probability of this happening, we calculate that to be 1/2 to the 5th power, or 0.03125. So that's roughly a 3% chance of us not ever getting an even number. So we're like thinking that's pretty low. So maybe this dice is not fair. So maybe it does favor odd numbers. So it's weighted weirdly, or corners are shaved or something. So there's something been done to it to make it kind of favor landing on an odd number. So what we want to do is we want to determine what is the hypothesis here. So if you think about the situation, what is the claim that we're trying to make of the situation? And when I say we, I'm thinking, put yourself in the dice maker's shoes. What is this dice maker claiming? This dice maker is claiming that, no, this is a perfectly fair dice. The dice does not favor either even or odd numbers. All right, so that is the claim, that this dice is 100% fair. So then a simulation could be run. So we take that dice and we're going to roll it 50 times. And then we see the results here in this histogram. So we rolled that same dice 50 times. And then the proportion of 50 rolls that result in odd numbers is given here. So here's where we're talking about proportions. So remember again, this is a sample. So if we were talking about P, this is the P with a hat, just kind of a heads up there. But again, what we want to do is we basically want to think about, okay, proportion. A proportion is created by ratios, right? Ratios are fractions, so we want to deal with some fractions. So if we look below, we want to talk about what conclusions we can make when we roll that die 50 times and we get 2 different situations. Let's say we get 26 odd numbers. How do we conclude if that claim is most likely true or false? Well, remember, if I scroll back up, if it's likely that it's likely true if the results can easily occur by chance. And on the flip side, it's most likely going to be false if the probability of the result happening is unlikely to occur by chance. So then if you're thinking about a dice, right, we have 3 even numbers, 2, 4, 6, 3 odd numbers, 1, 3, 5. So we're thinking if it's something that would happen by chance, then it's probably going to be about 50-50. So that's what I'm kind of looking at. If I end up doing this simulation and getting about a roughly 50-50 chance, then I'd say, okay, then yeah, maybe this dice is fair. But if I'm getting something completely different, like it's only a 10% chance this happened when it should be closer to 50-50, then I'm going to say, no, that's highly unlikely to happen by chance, then it's probably false. So what we want to do is we want to go ahead and just check some numbers. But wait, hold on. Let me make sure I explain the histogram before we actually do the numbers. In case it's been a while since you've heard relative frequency. To me, that's basically just a fancy way of saying kind of how many times it showed up. So in this simulation, rolling a dice 50 times, this isn't just rolling one dice 50 times. This is probably multiple occurrences. Like someone programmed a computer to say simulate rolling a dice like 5,000 times, and they compiled all of that data into this one histogram. So for example, like the proportion of 50 rolls that result in odd numbers. So like, let's say you got 38.38 or 38% of your roll was odd numbers. You saw that roughly like a little under 2% of the time. So that's kind of what this is saying. Okay, so then what are we doing in terms of calculations to help us use this histogram to give us a conclusion about whether or not the hypothesis is most likely true or false? So what we want to do is first think, okay, 26 odd numbers out of 50 is about what proportion? So our proportion is just basically 26 out of 50. So if we do 26 divided by 50, that's equal to 0.52. And then we want to find that right here, that's already marked here on our histogram for us. So 0.52 is right about here. And you can see, okay, well that did have a pretty high relative frequency. It's in that same interval where we have 0.16, or basically, that many of our trial, right, ended up with about 52% odd numbers. So this could totally have happened by chance. So when I see something close to that 50-50, I see it's happening pretty often, then I can say that this is most likely going to be a true hypothesis. All right, so there's my quick conclusion. And again, if you look, I would say the majority of our trials are roughly here around 50%. These are your three highest bars. So anything around that 0.50, 0.52 is probably likely to happen by chance. Now let's compare that to this let's compare that to 35 odd numbers now. So the first thing we want to do is figure out that proportion. So the first thing we're going to do is do the fraction 35 out of 50, and that's going to equal what equivalent decimal value? Well, that's 0.70, which you can see right here, handily drawn for us. So what's interesting about this is, wait, there's no bar. This didn't even happen in the trial. So if it didn't happen in the trial, could it really have happened by chance? Probably not, right? So in this instance, we can see, okay, looking at the histogram, there's no evidence it even happened in however many trials the simulation used, and it's nowhere near logically where we want to be with 50-50. So I'm going to say that in this situation, it is most likely false. All right, so there it is. Again, very unlikely to happen by chance, unlikely to pretty much happen at all. So it's most likely false. Okay, one last thing I want to talk about before we get into the U-try problems is right here, this little chart. Don't let this be kind of confusing. This is just basically a summary of your possible results, basically. So it should hopefully be pretty straightforward. So either you decide the hypothesis is true and you're right, or you're wrong, or you decide the hypothesis is false and you're wrong, or you're right. One of those four things is going to be true about the situation. That's just what this is saying. It's like you have four possible outcomes of your decision. So that's just saying, right, this is what could happen. Okay, so go ahead and now pause if you would like, and work out those U-try problems on the next couple pages. And whenever you're ready, hit unpause and we'll go over the answers. All right, so hopefully these first two are pretty straightforward, just identifying population and sample, not really saying anything else. So you can see the U.S. Energy Information Association, or the Energy Information Association in the US, is trying to estimate the prices of gasoline. So you'd want to figure out, hopefully, information about all the gasoline stores or outlets or stands, right? But they only had time to call 800 of them. So the population is all the gasoline outlets. Sample is just the 800 they called. Similarly, the next one, right? You're trying to figure out information about all the shoppers in the US, maybe thinking about Black Friday sales or whatever. But do you have time to survey everybody? Do you even know who the population? Do you know who actually went shopping? We don't know. So they surveyed as many as they could. So the population would be all the shoppers, and the survey is the sample, the 4,464. All right, next we're talking about parameters and statistics. All right, so this first one might sound like it's actually a parameter, but it's a statistic, because if you think about it, they're trying to talk about the median salary of statisticians in general. Are there only 1,068 statisticians in the world? No, right? There's tons. So that's why we call this a statistic, because we only surveyed a subset of all of the possible statisticians that are out there. Versus the next one, which you might have thought was a statistic because you're like, oh, it's just the mean of the people in Congress. But if you look carefully, we're just looking at the population of the 113th Congress. And if we found the mean of all of those people there, then that's a parameter, because we're dealt with the entire population of all the representatives in the 113th Congress. So careful, we have to really think about the situation. Last one, we were using the same simulation, so the same histogram from the last example. So you had to come up with your proportion, which is basically that decimal value. And then if you look back at the histogram, which I'm scrolling back up to, 0.48, again, very close to 0.50, so it's right about here. And you can see the majority of our trials ended there. So it's likely it happened by chance. So that's why I'd say, yeah, that conclusion is most likely true. The hypothesis most likely true. Versus the other one, which was what, 0.62? Right? Let me just check my number again. Yeah, 0.62. So if we look back up, sorry for all the scrolling. Here, 0.62 is highly unlikely to happen. It's kind of here toward the end, tapering off. Only about, a little over 2% of our simulation runs were actually getting there. So very highly unlikely to happen by chance. More likely to happen if someone, skewed the dice to lean towards the odds. So again, here are the answers to the last one. Most likely true for A, most likely false for B, because we were interpreting that histogram. So that sums up samples, populations, and hypotheses, and we'll be using these some more in our later objectives. If you have any questions, please let me know. Thank you for listening.